But that looks really ominous. It's just a black screen. Hello. All right, so we've talked a lot about one predictor. But like honestly, you're almost never going to put one predictor into any sort of linear model. It's not happening. Usually you're going to be interested in multiple predictors. You are going to put in only one predictor for your homework this week. Just one. Now in a multiple regression, you would have a formula calculated to relate your one outcome variable to your two or more independent variables. And in ANOVA, we're going to do the same thing. It's allowing us to investigate the effects of variables while statistically controlling for the effects of other variables. Now, I used slightly different language here, but really, remember, they're all the same. It's all the same thing. Oh, apparently, I'm waiting on multiple variables, and first I'm going to talk about centering. Okay, remember how the intercept, and later on more coefficients, but right now the intercept is all you know about. The intercept is always interpreted when all of your predictors are 0. Because that's how the math works. You have to plug in a 0 for your x in order to get to the y, predicted y. So when the values of the predictors do not include 0, that can make interpretation problematic. Like what we had a minute ago when our expected GPA when study time was 0 was negative 0.247. That's not possible because it's outside of the scope and range of our observed data. So here's an example. So to get around that problem, say you have a predictor that ranges from 100 to 300. There's no 0 in there. And so that means when you're predicting things, you're going to be predicting stuff happening way outside of the scope of your actual data. So when we get to the idea of centering, centering is just a fancy word that means subtracting a constant or adding a constant to every variable in your data set so that now it includes 0. And it just moves your regression equation or that linear equation around so that it's sitting within the realm of your observed data. If I subtract something from everything, it's not going to change my standard deviation, but it's going to change the mean. It's going to change everybody's values, but not the variance. If you want to center a categorical variable, here's an example data set. Here I have a variable of condition, and you see it's scored as 2 and 1. And we talked about this last week. So I'm going to just fly through it pretty quickly. So it's problematic that it's scored as 2 and 1 because if I run a regression, in this case, my R squared here is 0.137. My F test is telling me that I have significantly decreased my error by including that in the model. No problem so far. Oh, it's telling me so I guess I could actually read what's on my dang slides. I have not significantly decreased the error in my model. Now once I get here, if I interpret my B0, I would interpret my mean score on the final exam for someone in condition 0. That's 3.8. But like, there's no condition 0. So this is an invalid piece of information. That piece of information means nothing. This is significantly different from 0, but it doesn't mean anything. Because there is no condition 0. There's only condition 1 and condition 2. So I'm going to fix that by recoding everything. I'm recoding this by just subtracting 1 from everybody. Because remember, they were scored as 1 and 2. So I'm going to subtract 1 from everybody's score, and so I'll end up with 0 and 1 for my two groups. And so now, if I go to rerun this, my R squared is identical because my variance hasn't changed. My F test is identical because my sums of squared errors haven't changed. But now if I look at my B0 is different. My constant here is 5.4. So that's telling me the mean final exam score for someone in group 0, which I now have, is 5.4. And the difference between my two groups is 1.6 on my final exam, which is not significantly different from 0. But still, I want to be interpreting it in a logical place. So that's all centering means. It means in a dichotomous variable, it's going, neither of these two is 0. I would like one of them to be 0 so that I can interpret my coefficients correctly. It's a data management problem. What about with continuous variables? Well, honestly, continuous variables, it's the same idea. Remember how before I had 1 and 2 and I just subtracted 1 from everyone? Now I'm in a situation where I have a continuous variable. It's still just moving where the 0 is. So in our GPA example, our expected score when GPA was 0 was 355. But look, we don't have anybody in this data set with a GPA of 0, and SAT scores can't range as low as 355. And so if I recenter these things, I can get something that's a little bit more interpretable. Did you read the article, The Centercept, or are you reading that this week? I think you didn't read it. There's an article called The Centercept. It's in your readings for next week, or to continue your understanding of this week. And the idea of the centercept is that if your intercept tells you information and tells you different information as you recenter your variable. That's all. So my interpretation here of B0 is that people with a GPA of 0 have an average SAT of 355. But again, it's not very meaningful because I don't have anybody with a GPA of 0. So one way we can do that is to center at the mean. I got the mean of GPA just because I picked a random, I was like, where could I center it? I'll pick the mean. The mean is 3.07. So I'm going to create a new variable for GPA, and I'm going to create it by taking the old variable and subtracting 3.07. And now I have a variable where 0 for GPA doesn't represent a 0 GPA, it represents a 3.07 GPA. And once I've run this analysis, now my interpretation of B0 is that the average SAT score for people with an average GPA is 1275. Because before I had anybody who had 3.1 as their GPA, it now says 0. Anybody who had 3.2 as their GPA, it now says 0.1. Because I've subtracted 3.1 from everybody's score, everybody's GPA. So I can still use a value of x to get a predicted value of y, but we have to interpret them a little bit differently. Because when x equals 0, the math still works to get you to the right answer, but x being 0 really means that x is 3.07. So because I've centered it at the mean, what is the predicted y if GPA is 3.07? I would plug in 0. Yes, 1275. I would plug in 0 to get to that answer. So here the interpretation of y hat is when GPA is 3.07, we predict that SAT will be 1275. And now, just to be very tricky, what about y hat when GPA is 4.07? What am I going to plug in for x? Yeah, I'm going to plug in 1 for x, exactly. If I plug in 1 for x, I can solve it, and I get 1575. Which means I can interpret it like this. When GPA is 4.07, we predict SAT will be 1575. So I give you these examples to demonstrate that if you're working with variables that don't have zeros in them, that this is a very useful technique to get yourself into a position where you're able to interpret your coefficients more appropriately. If you're working with SAT scores as a predictor and their lowest value is 400 and you're trying to interpret it when it's 0, it doesn't make any sense. And you're going to be working down here in an absolute 0 coffee situation.
Wouldn't this create more work though in terms of interpretation? Because you will still get the meaning of the x when you look at descriptives. So that would only, because when you're predicting from this view centering, you have to alternate your, you have to adjust your input each time.
Mm-hmm.
Versus before when you were using 0, then you could just automatically just input that and adjustment.
Yes, but. So the question is, I'm going to try to reiterate it, but you catch me if I get it wrong. The question is, why would I want to center things? Because that actually just creates a lot more work for me. If I want to predict an expected score for somebody who has something of 100, then I'm going to have to convert that in my head first and then plug in the right number. And you're absolutely right. In that case, that's exactly what happens. However, when you're interpreting these sorts of models, these linear models, rarely do you actually use it to try and predict an individual person's response. Usually the way that you're looking at it is like you're looking at these and saying, is there a relationship here? And so the interpretations here of the constant, for example, is only valid when you're within that realm of possible responses. So the significance of your constant, the significance of your y-intercept, is only valid when you have variables here that contain 0. Just like with our group example, if this won't give me the mean and significance test of the group coded as 0 if I don't have a group coded as 0. So yes, it definitely creates more work for you if you're trying to do this kind of interpretation. Plug in a value that means something and get out a predicted value. But this, I'm really having you do in a scaffolding type situation because I want you to understand how these equations work. And I think once you would use them to sort of describe what's happening within your results, but you wouldn't use them necessarily for this exact purpose. Oh my gosh. Excuse me. I'm going to actually skip that. Other things on centering. Again, it's a tool for you to use. Keep it in your tool belt. Move things around if you need to. You don't have to. You remember learning about z-scoring? That was intro stats, where you find the mean and the standard deviation. You subtract the mean, divide by the standard deviation. And then everything's in standard deviation units. Centering is like half z-scoring. You're doing the same idea, you're just sort of moving things around a little bit to get to a more interpretable space. Never required, but always better to be safe to have them in that space, because otherwise you can get yourself in some difficult interpretation territories. Okay, now, the concept of centering being laid out, now, let's talk about multiple predictors, for real, this time. So, I have some example research questions for any sort of multiple linear prediction. So you might examine whether age and socioeconomic status are related to frequency of library use. It's just multiple predictors and one outcome. So I'm going to walk through an example with you. Again, I'm sticking with this publications data set, reminding you that they are fake data and old data, old fake data at that, before you see a salary of $18,000. Just wanted you to know. So here we have 15 fake people and their number of publications and their years of experience and their salaries. I bet I could scrape this data from EHE's website. Yo. That would be fun. We'll do a Google Scholar search. Okay, sorry, back on track. All right. So now, instead of predicting number of publications, now I want to predict salary. So let's look at how numbers of publications and years from PhD predict salary. I'm going to do both. With one or more variables, the goal is the same as it was before. We're going to get a predicted score for each person. We're trying to find the line of best fit through the scatter plot of points. We are trying to reduce error in our models. And so we're going to put both predictors into one equation. Our full model now has two predictors, where our full model has two predictors. That's all I wanted to say. So let's think about the pieces. R squared, sums of squared errors, coefficients. One of those three things is going to be different with multiple predictors than it was with two predictors, with one predictor. R squares are about variance in your full model and variance in your restricted model. I was going to try to make you guess, and I give up. I'm not going to make you guess. It's about variance, so you get one R squared value. Now with the F-test, the sums of squared errors for the regression, the sum of squared error for the full model, and for the restricted model, full model, restricted model, we end up with the same, only one regression, sums of squared errors, but our degrees of freedom is different. Now we have 2 degrees of freedom, because in our restricted model, we have 1 degree of freedom, and in the full model, we've used 2. 3. We've used 3. Intercept, slope 1, and slope 2. So that's why we have 2, because it's the difference between the 2. Now, for our coefficients box, now, instead of getting just 1 predictor, 1 slope, now we have 2 slopes. 1 intercept and 2 slopes. Yeah.
I have a question.
Yes.
So when we're looking at the R squared, that 62% is saying that 62% of the variance is explained by both time and numbers of publications together.
Correct.
Okay.
R squared is saying both time and publications together is predicting this much variance. That's exactly right. And then the F-test is saying, well, almost. I'll go through the F-test. This is the same. You just did my transition very nicely here. 63% of the variance in salary is explained by both time and publications. Now, what I want to show you here is that the R squared values in this model are different than they would be if you had done them separately. So this is me saying I ran this R squared when I just had publications as a predictor, my R squared was 0.45. When just time was the predictor, my R squared was 0.58. And together, they're 0.62.
Another question.
Uh-huh.
When we're saying when they're together, would that be the equivalent of saying like an interaction?
No. An interaction is a separate thing. This is just, these, we call them additive models because we're just adding together the components of the model. Wait, we're just adding together the coefficient. I know it's weird because we're multiplying the coefficient by a weight, but we're adding that final products. We're adding products together.
Okay, that's helpful. I think.
Oh, yeah. Uh-huh.
Are they controlling for each other in this model, or is it?
Yes. They are controlling for each other in this model. That's exactly right. Not in these, because here they're alone. But up there, in the top one, up here in the top one, they are controlling for each other. So it just means that you can't just run one and then run the other and then get the R squared and add them together. Can you see that that would be much too big? 0.58. And that's because they're controlling for one another in this prediction that they together are accounting for this much variance. If you think about it in a Venn diagram terms, all three of those pieces overlap. I think I have a diagram of that later. Now we're in the F-test, or this ANOVA table, and it's a little bit different, but the basic concept is the same. We're still looking at whether we've reduced error in the model. So But because of the way that the math works, do you remember how we have degrees of freedom and sums of squared errors both in the numerator and in the denominator? So what we're looking at here is whether the change in the error is like worth it. So we have two predictors in the degrees of freedom of regression. The degrees of freedom in this regression step is 2. So what we're basically saying is that is the amount of variance we have reduced, amount of error variance we've reduced, worth this sacrifice of the degrees of freedom that we have made to add them? Again, we're in a scaffolding space here so that you understand how this math works. And so, what the F-test really means here is, on average, does each parameter contribute to the model fitting? Yes or no? On average, because I have parameters here in this bottom thing as well, sorry. Number of predictors is my same idea of parameters. Number of predictors is like, I have, in this case, 2. I have both years and I have number of publications. So that's 2 more predictors. And it's in the denominator, so we're talking about it being per predictor. Or not per predictor, but like on average, do they all contribute? So the interpretation here is, on average, each parameter is contributing to the model fitting better than the restricted model, which is also called, the restricted model is also called a grand mean model, which is also called the model where you guess the mean for everybody. Now when I get to this table with my coefficients in it, the interpretation of the constant is the same as it was for simple linear regression. It's the mean value of the outcome when all of your predictors are 0. The expected score on your outcome when all of your predictors are 0. So when I create this regression equation, if I plug in 0 for time and 0 for publications, my expected salary is $16,791, which is significantly different from 0, if you care. So now with these other B weights, the interpretation is slightly different than it was before because we have to talk about controlling for the other predictor. So what I have here is the expected change in the outcome for a 1-unit increase in Y. That part's the same. Whoa, I'm sorry. The expected change in the outcome, which is Y, for a 1-unit increase in X, which is your predictor. That is exactly the same as it was before. But now we also have to say when we're holding constant all of the other predictors in the model. Time going up by going up by 1 unit, resulting in an increase in expected salary of $922, is only valid when publications is in the model and being held constant. And so here's my example. The average change in salary for an additional publication is $316, holding years from PhD constant. If you want an image of that, it's me and then Dr. Kim, who's in my program as well. We started at the same time, so our years from PhD is constant. And every time one of us publishes a paper, someone would walk into our office and hand us a $316 check. If it does not happen, that would be pretty cool. So if she gets 4 publications this year and I get 2, she would be expected to have an increase in salary 2 times what I would, because she has 2 times more publications. And our years from PhD are the same. I actually don't know if that's true. We just started at Ohio State on the same day. That's okay. Hypothetically, we'll say it's the same. So let's talk about this one, publications. So I've got 4 different ways that you can talk about this. Okay, 3 different ways that you can talk about this. Again, what I want you to remember is I'm handing you a box of tools, and I want you to take these tools and use them to tell your stories. So here are 3 different ways. Each one of them centers a different part of the argument. So here I say, for any given number of years post-PhD, the expected gain in salary per publication is $316, which means the same thing as, but has a slightly different feeling from, after controlling for the effects of time on salary, the effect of publications is $316 per publication. So in this one, I'm just changing things around. 2 people who got their PhD the same year and who differ by 1 publication be expected to differ in salary by $316. However, that number is not significantly different from 0. When you are working on your homework assignment, feel free to take any of these sentences and copy them in and change the variable names to your own.
But if you were looking at time instead, say for every additional year,
Yeah.
that difference,
Keep-
that would be statistically significant.
That would be statistically significant. How would you do that? For every additional year, what else do you need to say?
While holding the number of publications constant,
Uh-huh.
you could expect an additional increase in salary by 922.
Yes. I don't even know if I have that one. Yes, excellent. So every additional year, holding number of publications constant, you would expect to increase by $922. Yep, and there's just 3 different ways to say the same thing. So I'm just demonstrating once again that this multiple model, this model with multiple predictors, is not the same as running one model and then the other model. Here are the coefficients for time and publications when they're separate. And here's the y-intercept when time is the only predictor, and here's the y-intercept when publications is the only predictor. They aren't the same. One of these goes up and one goes down. Right before I was accounting for number of years, once I got another publication, they'd hand me $500. Now you're accounting for years, now I'm only getting $300. Any ideas why that might happen?
Is it because in this omnibus they're accounting for the overlap interactions between the two?
You're accounting for the overlap between the two, exactly. And time and publications probably correlated. Someone who's been away from PhD for 1 year probably has fewer publications than someone who's been out for 10. And so, however publications correlates with salary, time is also going to correlate with salary because they're correlated with each other. So by controlling for one, we're able to look at the unique examination of the other, how the other one predicts. Susan, are you telling me that you're not here? Yes, okay. Now, if I want to plug this into a regression equation, we use exactly the same steps as we've done before. I have my intercept, I have my 2 slopes, and then I'll have an x1 and an x2. So now we're in the quiz. But again, it's not a real quiz. We're doing it on paper again because I didn't program it in the computer. So we're going to do it on paper. This is real data. This is the same data set that I have for your example data if you would like to use the example data for your homework. So in this grad student survey, we have selected data from students who are post-candidacy in 3 different areas. I have social behavioral sciences students, I have physical and mathematical sciences students, and I have students in the humanities. And they were asked, how many research presentations have you made at regional, national, and international meetings? It's a sum, a total. So I have a mean of 2.7 and I have a range of 0 to 23. And then my research question here is, students in which program present more often? So to do that, I haven't talked to you at all about how this works. So sorry, we'll see how you do. What I have here is students in the social behavioral sciences, students in the physical and mathematical sciences, and then I have the constant. What's the constant going to be? Can you make? Yeah, whoever's in humanities. So now, hang on one second. Let me get this.